Well, our final chapter is on smoke control and management systems. Can you believe it? We're almost done with this class. All the way back in the beginning, I talked about how there are three categories of fire protection systems. Alarms, and alarms have their origins all the way back to, we know, as far back as Roman times, with the use of human beings as fire watch. In colonial times here in America, in Boston and in New Amsterdam, later called New York, fire watch was in their laws. So we know that this system of warning, though we have modern systems that have come, way forward, but they have their origins very far back with the ideology of we got to warn people. And then the second category of fire protection system is our suppression systems, which we've spent the bulk of this class talking about because there's so many different kinds, some of them newer, some of them older, all the way back in the 1800s. The ideas of some kind of a sprinkler system, some of them as crude as some pipe into some buckets with holes in them. But eventually we have the modern fire suppression systems of sprinklers, gas systems, CO2, all of that. Well, in the 1800s, there were ideas about trying to get smoke out, and in the 1900s, but they really weren't at all similar to what we have today. Smoke control and management systems is more of a modern thing. It's the newcomer of our three categories that really took a boost in the 1970s, and we'll talk a little bit about why with that in a second. So, smoke and toxic gases are going to migrate throughout the fire area, and even when we have a very small fire, but it can be in something that's very hazardous and spreads toxic gases and smoke particles throughout the building, which are extremely dangerous for human beings. So the smoke is also, we know heat rises, and the smoke goes with the convective flow, and it'll go up stairways, corridors, hoistways, and of course, if we have an atrium or some kind of an opening, it's just going to flow from one floor to the next. So the spread of smoke and toxic gases is usually what kills people. It can cause as much damage and injuries and death. You know, we had a little smoke issue here once, and it was all my fault. It's a long story. I won't go into it. But it took weeks to get that smell out, with fans and Febreze. God, we went through so many cans of Febreze just trying to get the smell of the smoke out. So the damage to the building from smoke can be extensive, but the injuries and death is what concerns us the most. More people die from smoke inhalation from being burned. You know, we use the term, oh, they burned to death. Most of the time, they didn't. Like the MGM Grand Hotel fire, which we talked about early on in this class, 85 people died, 79 of them from smoke and gases only. They weren't even exposed to the fire. It was the smoke and the gas. So this is a deep concern, and is one that, because of the MGM Grand Fire, and also the rise of more and more high-rise hotels and apartment dwellings and more malls, that kind of was a thing in the 70s that became more and more common, covered malls. These types of structures and designs led us to require more and more smoke protection. So let's get into it. Well, where is it required? What type of buildings or occupancies require smoke control systems? Well, the California Building Code has a whole chapter on it. Chapter 4 tells us that amusement buildings, atriums, covered malls, open malls, I3s, high rises, stages, underground buildings, these types of facilities, they need smoke protection. So what do these buildings all have in common that causes the need for smoke control? Well, two very important things. These buildings have issues with rapid smoke spread most of the time because they have atriums or open floors or openings that go from floor to floor. And the other thing they all have in common is evacuation buildings. Now, most buildings are significantly compartmentalized to inhibit smoke travel. That's why there very rarely is it allowed for openings from one floor to the next other than a stairwell, and usually in commercial buildings there's always doors on the stairwells. But so we do that to inhibit smoke travel. But many buildings, like the ones we just mentioned, don't have, or they do have openings from floor to floor. So smoke control requirements exist for those occupancies that have significant evacuation challenges. Think about I-3. It might not be built like an atrium, but we don't want to just open the prison doors and let everybody escape. So there's evacuation challenges. They're gonna, if they have a fire, they have a certain way of evacuating people, and they're going to do it in a controlled way. They need more time. Smoke control helps them with that. Now, most of the buildings we just talked about, what they have in common is an atrium. Not all of them. All of them have evacuation challenges, but most of them have atriums. So what is an atrium? Let's make sure we all understand that. An atrium is any kind of building or space within a building that extends vertically through two or more floors. So that doesn't include stair shafts and mechanical shafts that are enclosed in rated construction. But we're going to, for sure, require a smoke control system if the atrium is open to three or more floors. We might, in a two-story atrium, require it like in a mall or in an amusement building. If you're on Pirates of the Caribbean, well, technically that's 2 stories. I don't know if you realize that. It's a 2-story building that it's encased in. But, it's a place with extreme evacuation challenges, an amusement ride. So we're going to require it there, even though it's only 2 stories. So assembly halls, ballrooms, shopping malls, sports arenas, all of these kind of places that are very large volume places are going to include smoke control if they meet the definition of an atrium, or if they have other issues that might lead us to require it. So here's a great picture of a typical covered mall. Not as popular as they used to be. Everybody likes the open air malls, the outdoor malls nowadays, but these were very popular at the end of the 20th century. And the problem is, see how it's open from first floor to second floor. There's tons of people. The exits are not necessarily spaced so close as you would in a normal building. And so as a result, they're going to require smoke control. Chapter 9 in the Fire Code and the Building Code are going to give us specifics. In 914.3.6, we're going to have the specific requirements that are going to say what and where, not the how, but all of the what. That it's going to say this is where it's required. So all portions of high-rise buildings have to be protected with smoke control systems. And smoke-proof exit enclosures, every exit enclosure has to have some kind of smoke protection as well. And what we're talking about is large stairwells in high-rises and things of that nature. So the goal of a smoke control system is to maintain tenable conditions for 20 minutes. to protect life, but not necessarily to protect the property. We're trying to get people out safely, give them more time. So they're going to keep the smoke 10 feet above the highest occupied space by the many usages that we're going to talk about, or the means that we're going to talk about. So they also are going to try and prevent smoke from migrating from one part of the building to another part. The goal is to accommodate a fire of 5,000 BTUs and keep the room from getting engulfed in smoke. So how are we going to do that? How are we going to provide that tenable environment and keep the smoke from banking down? Well, there's three basic ways we're going to do it, but we talk about smoke control and smoke management, okay? So smoke control is the mechanical systems that pressurize areas of buildings with fans to limit smoke movement. Smoke management, with that, we're talking more about the passive and active systems used alone or together to alter the smoke movement. So smoke management systems were mostly developed in the 70s, and again, that MGM fire played a big part in raising the need, and some other fires that happened around that time. When 79 people die just because the smoke went right into the stairwells, into their hallways, and people were found who were trying to escape, lying dead, unburned, unscarred, just dead from smoke inhalation in the hallways. So the three ways is, first one is passive. We're going to use passive designs like walls, bulkheads, doors, partitions, draft curtains, high ceilings. There's a reason why when you're in Walmart, Costco, Bevmo, Home Depot, Lowe's, that high ceiling in there, it's there for multiple reasons, but one of them is to keep smoke away from the people. And you're going to see other passive things in those kind of buildings. I'll show you a picture here in a second. So they seal the floor openings to create barriers. They use fire-rated constructions. So here's two examples of passive. Passive is where we just use features as part of the building to keep the smoke compartmentalized or from going from one part to the next. So the picture on the right is a manually operated smoke and heat vent in a stairway. You pop this thing and it allows the smoke out. The draft curtains that are commonly seen, like in the picture on the right, and I took this picture in Costco. So draft curtains are oftentimes just some partition that'll hang down 4 or 5 feet from the ceiling. But I also want you to notice the skylights. Well, those skylights are not just there to bring in natural light. There's many different kinds of passive protection with skylights. Some of the skylights are made in such a way that they have a fusible link, and the fusible link melts and pops, and the skylights are spring-loaded, and they'll pop open and allow smoke and heat out. Others are made with a kind of plastic that rates at a certain heat, and that are rated to melt at a certain heat. So when the heat builds up, they start to drip, and eventually they melt, and it allows the smoke to passively leave the building. So these are examples of passive smoke protection. Now the other kind is active design, and with those there's a lot of different ways they're going to do it, but the main ways are they're going to use mechanical systems to either exhaust, pull the air out, or pressurize, push the air in. So they're going to pull it or they're going to push it. So with these, choice of design, passive, active, or a combination of all of the above, it's just going to depend on the factors of the way the building's built, the architectural features and things like that. So that physical design and the way the building's built. Think of the hotels you've gone in that are multi-story hotels, and you go in the lobby, and there's many, many floors that are open, and it's beautiful. It's really cool looking, but these are atriums that make that hotel lobby very dangerous. So stairways, elevators, air shafts, ductworks, these are obvious places where we need to have some kind of a smoke control system, and atriums. But the less obvious, we want to also make sure where we've cut holes in the wall, we need to seal that. Unsealed construction can be a place where smoke can go from one part of the building. So there's things like that where we want to design it so it can't do that. Wherever we run utilities from one floor to the next, they cut these big holes. Well, they need to seal that. So smoke spread depends on a lot of different factors. And this is why, especially in these large buildings we're talking about, we need an engineer. Because there's buoyancy forces, there's stack effect. Stack effect is where the hot air rises to a point that it starts to cool off, and it hits cold air, and now it just stops, and you have this big stack of smoke, and it won't go any higher until the heat builds up to take it to a higher level. Climate, ventilation, the HVAC, which is the heating, ventilation, air conditioning, that all of these things are going to be factors that an engineer needs to mathematically figure out along with architects and others. So the goal is to maintain that tenability by mitigating smoke spread or containing it. So these systems can be standalone. There are places where you might have a stage, and maybe that stage is like an outdoor, kind of partly outdoors, partly indoors. These are not very common, but every once in a while you'll see them. And the stage part is actually enclosed and can be closed. But stages oftentimes will have 2 to 3 floors of opening over the stage. And it's where they put the curtains and set decorations and all of this, and it goes up and down. So they might have smoke control just for that, but not sprinklers, not standpipes, not alarms or anything else. That's pretty rare though. Usually smoke control systems are going to be integrated with the rest of the system. So 100% outside air for positive pressurization, 100% exhaust to the outdoors to contain or relieve smoke. So remember I said 3 methods. We're going to contain it. Usually that's done with passive. We're going to remove it, or we're going to oppose it, that smoke. So most of the time, especially in these bigger buildings, it's going to be a combination of all 3 or 2 out of the 3. So let's talk about containment. We can contain it by passive means, but we can also contain it by pressure differentials. So pressure differentials... Hey, I'm sorry, I got a phone call from Captain Kintaley from Oxnard Fire Tech, and I had to answer that. So forgive me for a little interruption on that if it seems a little weird on the video. So again, they use pressure differentials to contain the smoke in certain areas or keep it out. So if you pressurize a hallway by having fans above pushing air in, when somebody opens the door, they're going to feel a blast of air, and the smoke is going to be pushed out. They will be able to go in. The door will be forced closed behind them, but the smoke won't come in with them. So pressurization is one of the most common methods of smoke control, especially in high-rise buildings and our larger buildings. So the codes are there, NFPA 92, 92A, 92B. These are all the standards, but in Chapter 9, that's where we get the codes telling us what to do. So here's an example of how this works. It prevents or reduces smoke intrusion into those egress stairways. These mechanical fans pump the outdoor fresh air in and create a pressure barrier. So here's a close-up of that fan and the ductwork that's going in, and on the other side of that wall, here's the grill where that air is being pushed into this stairwell. And it pressurizes it so that when people enter the stairway at the different floors, the smoke doesn't come with them. Now, they got to make sure the door closes behind them, and usually that's done automatically with the door. It will force it closed, but if it doesn't, the people need to close it. So keep that smoke out. They work well when combined with smoke removal or smoke relief on the affected floors, where other kinds of fans are pulling the air out instead of pushing air in, and they're pulling the air out of the smoke floors to evacuate the smoke. So all these different things have to be considered by the engineer when they're making them, and they're very common in high-rise. And in the high-rise, they've got one of the things that they'll do is these floating zone floor-by-floor pressurization, where they positive pressure floors above and below and stairways, and negative pressure, which negative is pulling out the smoke-laden air on the fire floor. So the air is going to move from high to low pressure. So it creates what they call a sandwich effect or a containment method. So I got a great little drawing on it on the next slide, but this method employs the building air conditioning system to pressurize the non-fire floors and a relief or exhaust system on the fire floors. Of course, this all has to be integrated with the alarm system. It's electrically controlled. So because fires take out the electricity, of course, it's going to have some kind of generator backup, make sure it works even if the building's on fire. So here's that illustration, and you can see where the positives are positive pressure, where air's being pushed in. The negative is where air's being pulled out. So it's a push-pull effect which keeps the fire sandwiched and the smoke onto 1, 2, or 3 floors, but hopefully above and below, that smoke is not going into those other areas. So they do that with these big, huge mechanical fans and the vents where it pushes the air into the corridors to create this sandwich effect pressurization. Now, they do this also, similar kinds of systems in elevator hoistways. So it's very similar to the stairway systems where mechanical fans are going to pump outside air into the hoistway and create a pressure barrier, because if you think about it, the elevator hoistway is just like a chimney, and it'll take that smoke throughout the whole building. So some designers think they should be part of a complete smoke management system. Sometimes they're standalone, but there are others that are concerned about elevator doors being open. So elevators are automatically recalled to the bottom floor, so that hopefully won't happen. Now, another thing that they do with pressurization is refuge areas. Now, these are common in high-rise buildings and buildings with handicap or ill people, like hospitals and large convalescent homes. They'll create refuge areas, and a lot of times they're right near where the elevator is, and they have doors that automatically close, very thick fire-rated walls. The ductwork will automatically close so smoke can't come in or go out, and they'll pressurize that room with fresh air, hopefully giving the firefighters time to suppress the fire and evacuate these people in a safe manner. So these are oftentimes near stairways or near elevator lobbies. The refuge areas are going to have that fire-rated material, and they're holding areas for people who need assistance. Now, smoke removal, instead of that pressurization, these are best suited for large volume spaces. So we're going to see big openings up on top in a mall or a big atrium where they're going to pull smoke out as fast as they can. These systems are very expensive to build, very expensive to engineer. They're best suited, again, for those places like the Staples Center, a large high-rise hotel with a big atrium or lobby. So they create tenable environments by pulling the smoke out in the lobbies and the refuge areas. Now, lack of restriction causes other problems in addition to large amounts of smoke gas. So if they have delayed activation of sprinklers or detectors, this can be a little bit of an issue. Unpolluted air from a lower level is pulled up at a slower rate than the exhaust system rate. So they're going to feed the air in, because if they push too much air in, they're going to encourage the fire to grow. But they want to have fresh air coming in below and then really big fans pulling air out above. So the mechanical fans near the upper level are going to exhaust the smoke out. And very typical in these big atriums. We're also going to do containment, and we can do this with airflow. So not only do we push and do pressurization, not only do we pull, but we can contain. And that's kind of what we were talking about with the sandwich effect. But in railways, subways, big tunnels, imagine the channel has something of this nature. They can control smoke across openings when pressure differential strategies aren't going to work. So it's least common, but it's usually used in these places like subways. The problem is you're infusing a lot of air, so you risk feeding the fire. All of these things have to be done by engineers. And these are specialized engineers. Not just any engineer can do this, because there's so many factors that have to be figured out. The amount of energy that's needed to power the system. We're talking about cubic feet per minute air movement. How many BTUs is the fire putting off? All of these things, it's very challenging. And the codes give a lot of operational requirements. The standards help, but when it comes right down to it, you need an engineer who figures out the best way to do it. And of course, it's very important to integrate these systems with the alarms, with the fire suppression, and the smoke control all working together. So without those other systems, the smoke control systems would get overwhelmed quite quickly. So when they're going to design them along with not only our fire protection systems, but our HVAC, our elevators, our backup power systems, all of these. So high-rise buildings, complicated, super complicated in the fire protection and the way the building's built. So the design involves smoke control, sprinkler zones, detection zones, water pressure at the lower levels and at the higher levels and in the middle levels. So much calculating. More math than I ever want to do. I hate math, and I know a lot of you do too. This is for those math engineer geeks that they think about building a bridge and they get all excited, and the rest of us go, how would you even do that? I wouldn't want to do that. So engineers, they're going to put these things together. So that activation is going to be tied into the alarm system, and the alarm system is going to turn on the smoke control system. The sprinklers are going to be turned on by the heat, and all of these things, they're all going to work together. So a lot of times, the smoke control system going off and the sprinklers turning on needs to shut down the HVAC system so they're not feeding air in. So HVAC systems can be used as part of it, and they can be a deterrent to it. So we just don't, we want somebody super smart. You want the guy that builds the bridge that you're going to drive on, or designs the system if you're going to live in a high-rise apartment. You want that guy that's really good with math, not the one that got an award for trying. You want the best, right? Smoke detectors are usually in the elevator lobbies, and they're going to be throughout the building that initiate a lot of this control, doors closing, vents opening, some vents closing. They require battery or usually generator power backup. So here's very common in atriums. We're going to use beam detectors to detect smoke particles in the air, and then that's going to set off the alarms, turn on the smoke control, and then if the heat builds up enough, the sprinklers will turn on, and they're all going to work together. The smoke control is going to be related to the fire control panel, but it's going to have its own smoke control panel as well. And they're usually in a room that looks somewhat like this. It's a big interface with, we talked about addressable systems or systems where the firefighters can talk to people on different floors, an intercom system. All of this you can see in this picture on the right. Smoke control system panel, alarm system panel, that voice system, all of these things working together. And usually they'll have a room dedicated to this. It's the fire control systems room for high-rise buildings. When they're built, we're almost done here. When they're built, they need acceptance testing. So design professionals are going to design the system, but they're also even going to develop detailed test plans. The testing is going to occur as they're building it and after all the other life safety and fire protection systems are tested and approved. The testing is similar to the other fire protection systems. You've got to show that it works. Little factoid here, the Staples Center never has passed their smoke control system test. Yes, they have people coming in it. Not right now because I'm making this recording during the COVID-19 crisis. But Staples Center has stuff going on almost every week. And every time they have people in the arena, there has to be firefighters on duty in the building. It's great overtime for the firefighters, and the Staples Center says we can afford that. It's more complicated to fix the system than to pay LA City Fire Department to have firefighters there every night. So, never passed. They've tried it and tried it and tried it. I read an article in the LA Times recently that it's still not working. So, yeah, that's a bummer. But they're getting around it by paying for Firewatch. The functional and integrated performance has to be tested. Does it respond in the time it's supposed to? Does it pull out the smoke the way it's supposed to? Do the doors open and close the way they're supposed to? It's not just is the air moving, but is all the integration going on? Do the doors close that are supposed to close? Do the dampers close that are supposed to close? Does the HVAC turn off or on, whatever is required? Sometimes you use artificial smoke or fog to help visualize it, but it doesn't actually prove that it works. So all the tests have to be witnessed by a fire protection inspector and the engineer and the team that installed it. So they not only have to do that to prove that it works when they finish it, but then they have to do annual function and performance testing to avoid disrepair. So they need to make sure that it still works. Generators and these types of systems and then the pumps related to the sprinklers, they're subject to a mechanical failure. They need to be run on a regular basis. The fuel needs to be changed on a regular basis because it gums up. So different states, different local jurisdictions have rules about how often they have to be done. Here in the state, Title 19, the State Fire Marshal's Code, has rules in there about the testing of smoke control systems, how often. There's some things that are visual, like we've talked about, and some that they actually run it. So these are performed by the owner's personnel, but usually they're going to be witnessed by fire department personnel as well. We don't do the test, we witness the test. Remember that. I've mentioned this a lot in our fire prevention course. Never, ever touch the equipment. It's not your job, and if something breaks, they're going to blame you. You witness it, you visualize it, you document it, and you do all of that. So let's go through. You can turn it off here if you don't want the summary. I got 3 little slides on summary, and then we're done. The goal of smoke control and management systems is to provide a tenable environment, giving more time for occupants to exit the building and get out without being subject to the smoke and gases. The 3 general methods are containment, exhaust, pulling it out, or opposed airflow, pushing fresh air in, so pulling and pushing, containing. The choice is going to depend on the engineer and the design and architectural features of the building. It's common for large volume spaces, and we talked about atriums, high-rise, amusement buildings, I3s, things of this nature are where you're going to see a lot of smoke control systems. The smoke and gas need to be kept from flowing from one part of the building to another part, so they use them to do that. It's extremely important that smoke control systems are interconnected with the rest of the fire protection systems and the HVAC and the elevator systems and the backup power systems. So depending on what systems are involved, some things we're turning off, some things we're turning on. All of that is done by the alarm control panel. So we need to make sure we've got all adequate equipment and that it all works together. It can be really, really, really complicated. Lastly, the design of the smoke control and smoke management systems is going to be done by a design professional, an engineer. Hey, we want the guy that graduated, magna cum laude, the valedictorian of their engineering school that's designing these kind of things, because the way they're designed has a lot to do with the way they'll work. Then they need to be installed properly and maintained properly. The maintenance crews and the installation crews in the state of California, they have to be certified to do this kind of work. So they're going to provide the building occupants, the firefighters, a tenable environment necessary to evacuate, relocate, or stage during a fire emergency. And that's it. I'm sorry this was a little longer than I wanted it to be. That kind of seems to be a common thing with me. But I'm going as fast as I can to give you all of the information you need. Hey, we're almost done. We got one more little week, your final project, and one last little quiz, and you are done. So good job in making it so far. Have a great day.